Well, good afternoon and welcome to the Cosmology session, and Viktor will start.
Yeah, thanks a lot. Thanks to the organizers for putting together this conference and giving me the opportunity to chair this session. So I'll start. I'm not kind of new to this format, so my understanding is that my goal is also to review a little bit and put some broader context of the field of formal cosmology, as we call this section, and then I'll briefly, after doing this, after giving my perspective at least on where this field is going now, I'll give a very brief summary of this two papers, one of which appeared very recently on the topic of Bra-ket wormholes. And if you don't know what is a Bra-ket wormhole, I will introduce. Okay, so we'll start with this status review, and then to me, what is the formal cosmology? Well, it is more or less understanding the theory for the initial state of the universe, and ideally, because we're string theorists, ideally constructing some holographic just meaning microscopic, description of cosmological spacetimes. And one of this class of ideas, I would say, that we'll focus on today is what's called the no-boundary state. And this Bra-ket wormholes, to be introduced, is yet a particular subclass of this no-boundary states. And then, after introducing these things in the research part of my talk, I will construct Lorentzian Bra-ket wormholes in two-dimensional models of gravity, and then we'll discuss briefly some open questions and how we can make progress on these big problems. And you can interrupt me anywhere in the middle of the talk. I think I might even finish a bit faster. I'll try to let other people have more time. We'll see. Okay, so very briefly, what is cosmology? What's our universe is doing? As far as we know, our universe was expanding. Okay. And important is cosmology is one of these rare disciplines where we can actually hope to measure some predictions of quantum gravity. Okay, unlike probably in some black hole physics, unfortunately. And in fact, we already did. Okay, so there is this period of evolution of the universe that we understand quite well, experimentally and theoretically, in particular that creates cosmic microwave backgrounds and then some cosmological perturbations of dark matter that lead rise to creation of galaxies and stuff like this. And according to the best theory that we have now, there was also a period of inflation, okay, the one in red, which is a period of exponentially fast expansion, where the space-time was close to de Sitter space. That's why I call it quasi-de Sitter expansion. And the idea is that there were some quantum mechanical fluctuations of gravitational field in particular during this period of inflation that gave rise to this cosmic microwave background anisotropies that we observe. Okay, so that is important, I think, for us conceptually as a field to have in mind that we actually tested that gravity is quantum. Well, if this theory of inflation is correct, which so far is still a hypothesis, but the dominant one. Okay, so in fundamental cosmology, we often focus on this period of inflation because, partially because it's close to this de Sitter space, so it's a more symmetric period as the rest of evolution, but also because this is the period where perturbative quantum effects are important. And more importantly for these fundamental questions is what happened before inflation. Okay, so for most observational consequences, it's not so important what happened before inflation. But for us as theorists, for us as attempting to construct the fundamental theory, of course we want to have a full description. So we also want to understand what happened before inflation, assuming that inflation itself happened. Okay, and ideally we want to have some microscopic theory, a la ADS safety, right, or some full string theory description. Good. So that's what I just said. Now, why do we need potentially for this theory of initial conditions? We need some more understanding that we can get from just semi-classical gravity. Well, actually, there are some theorems that say that if we consider this inflationary spacetimes, but I said not exactly this iterator, but kind of close to this iterator, they always have a singularity in the past. Okay, so kind of classical, semi-classical GR breaks down. And then a pure de Sitter, it is a geodesically complete space, so I wrote down the metric here, but the geodesically complete space, it has not just, time goes upwards here, not just has this expanding part, but it has this contracting part. That is kind of weird from a cosmological point of view, so really, when we say that inflation is well approximated by de Sitter, we talk about this expanding part, and this contracting part is maybe on some, it's not so clear what to do with it anyway. So we need some, we likely need to understand some quantum gravity effects, some UV completion of gravity to develop this theory of initial conditions. But which also gives us a potentially an opportunity, an observational window on these even more complicated non-perturbative effects, okay? Good. So let me quickly summarize what is the status of holography as applied to de Sitter space or to cosmological spacetimes. So de Sitter seems similar to analytically continuing under de Sitter space, and actually it also seems similar to black hole spacetimes, which I will explain in a moment, because it's a less sort of trivial statement than this one. But so far, I would say that we're lacking any concrete holographic models. There are some proposals, but I don't think there's anything that many people would agree that definitely that works and definitely doesn't have any big conceptual issues. So regarding to this relation to ADS Schwarzschild space-time, so here I drew the Penrose diagram of de Sitter space, and you see that as a Penrose diagram, it actually looks identical to ADS Schwarzschild. So you may say, okay, that inspired people to propose some similar, also holographic treatments. But here, there's no way I can summarize all those attempts. I just say in words, right, that there are kind of two schools of thoughts when people think about constructing holography for de Sitter spacetime. One I will say global, when we try to explain this entire global region. Okay, so there is, of course, it's a Penrose diagram, so exponential expansion that is, say, drawn in this cartoon is hidden, right? But, we should keep in mind that when we go up here, this side of the spatial slides, this is what grows exponentially fast, okay? So the global idea is to try to actually explain what happens in this almost all of this region. Not that there is not, from the causal structure is clear, there is not a single observer that can measure anything on this slice, but we can consider some meta-observer that measures, the question measures what? So within this global approach, there are also there is important bifurcation. We can discuss the wave function. There is some state of gravitational matter fields, some on this slice, and this is what is the closest, technically, to what we do in ADS CFT, where we fix some sources and basically we fix all the fields that we have on the boundary of space-time. So here, this future boundary, there is no boundary for the Sitter space in the space-like direction. There is just a sphere, as Penrose diagram reported, there is S2, S2 shrinks to 0, but there is no boundary here. The boundary here is in the future. And imposing similar boundary conditions as we do in ADS CFT implies computing the wave function of the universe. While sort of closer, wave function is not observable, closer to what people actually measure in cosmology is computing some in things like correlation functions. Okay, and this is a very different thing, and that will be important in my talk in particular. And then a local view is that say, well, we should not imagine any meta observers, we should just imagine what a single observer living in this space-time, sort of like us now, can measure. And then that it will be restricted to this static patch, this triangle here, that is shielded, the rest of the space-time being shielded by the cosmological horizon, in some sense similar, but also in some sense very different to the black hole horizon. And then it's less clear what are observables, what good observables we can construct here, because, okay, there is no point where gravity is weak. Okay, now let me talk about what are the proposals for the initial state. Well, I'll actually talk only about one proposal, which is the no boundary proposal of Hartle-Hawking, and it's an old idea from the 70s, but it got, I think, it getting more motivation from what we learned about ADS-CFT, because we learned in ADS-CFT that gravitational path integral smooth geometries, and recently we learned even more that including non-trivial topologies gives us a good approximation, okay, to the more fundamental theory, which, okay, in the case of ADS-CFT is given by a boundary CFT. So direct generalization of this idea is also to consider some smooth geometries in a cosmological setting. So original prescription of Hartle-Hawking was to calculate the wave function. Okay, then remember I mentioned that within this global approach we consider the wave function. That is, we consider actually not no boundary. We consider geometry with one boundary. So this boundary is in red. It has some Cauchy slice on which we want to determine the state. Okay, and then the idea is that we fill in the same way as we do in ADS-CFT, we fill in the bulk with some smooth in generically complex metrics. Okay, that are generically off-shell, but on classical saddle points, if they exist for such configuration, they would consider the solutions of Einstein equations. So we can take, say, four-dimensional pure de Sitter space, where we just have positive cosmological constant and Einstein-Hilbert action. Then there is a solution, which I already wrote down. There is a sphere, the spatial slice is S3, so this red circle will be an S3, and then it's expanding exponentially. And then the no boundary geometry would be not this global de Sitter space that I drew before, but rather this. If we go in a time contour, at some point at t equals 0, we go in the imaginary direction, okay? And then we terminate our contour at I pi over 2. So this part is actually half of an S4. So there is no, this space-time is completely smooth and kind of drawn over here. So there's some Euclidean half of S4 that then is glued smoothly to a Lorentzian evolution, okay? So the outcome of this calculation is that the wave function has some amplitude, which is, I'm dropping some order 1 numbers here, but it goes as a cosmological horizon area, okay? Here there should be cos ht, okay? Sometimes I'm sending h to 1, h is the theta radius, okay? And then there's some phase. Very good. Now we can promote the solution to a slow roll inflation. What is a slow roll inflation? Very quickly is that we have not just the Sitter space, but we have some scalar field with the potential. This potential is relatively shallow, so for some time this field is like slowly moving on the potential. So we have something very close to this cosmological constant. And then we reach this red point. Red point corresponds to this red circle that is kind of our boundary. And then, say, the field fall down, and then we transition to some other cosmological evolution, accreditation, domination, whatever. So we really focusing on this region where the potential is almost flat. And then this no boundary state can also be constructed. I think Oliver will talk in more details about this kind of states. But the punchline is that now our wave function, this factor over here, gets translated in something more complicated. It gets translated in the horizon at the point where we transitioned more or less from Euclidean to Lorentzian region. Okay, that is the brief description. It can be said, but there is a nice review by Juan Maldacena recently this year, where he reviews this in more details that you can look to get to read up on this more. But I just say that there is an important problem, that this way we get a probability distribution for this transition point. This transition point now becomes a dynamically determined question, okay? And the probability is actually exponentially large for having this V of phi star as small as possible. That basically want to move this blue point to as close to the red point, which is a very short inflation, which is inconsistent with observations, okay? Good. Oops. Go back. So the punchline is that this Hartle-Hawking proposal looks nice, but it has this phenomenological problem as applied to inflation. Now let's discuss two-dimensional gravity, which is my example for the rest of the talk. So it can be thought of as, it's not so remote from a 4D world, because it can be thought of as a KK reduction of the Sitter-Schwarzschild solution, which has S1 times S2 special topology. So there's JT gravity, there's some two-dimensional gravity, where we have, in addition to metric, we also have a dilaton field, okay, with this simple coupling to the metric, and then we can also have some matter fields. And then there is this phi naught, which is basically in the four-dimensional sense, it is the horizon area. So there's also a Hartle-Hawking solution that has a very similar form as you see here. Now it's just this spatial slice is just a circle, and then dilaton has some solution. Same contour as we had for Hartle-Hawking. And there's still an issue. Okay, so there's a nice solution, classical, but there's an issue which is now we cannot apply, experiment to this two-dimensional gravity, but there is a theoretical self-consistency issue, sort of similar to black hole information paradox. Basically, if we add some CFT matter to this setup and compute an entanglement entropy of this matter in some subregion, because gravity is dynamical, we need to use what's called island formula that was actually reviewed today in the morning. Now, the details are in the paper. I'll just not going to take you through this drawing. This drawing represents some island configuration. But the punchline is that we can compute these entropies of various components of our matter fields, and they violate what's called strong subadditivity condition if we take the interval that's large enough. And strong subadditivity condition, it's a kind of a theorem proven in quantum mechanics. So any quantum state, for any quantum state, this inequality, this object should be positive, okay, for whatever subsystems we have, and we calculate it and we get it negative, okay? So the theoretical problem. So, punchline, we do not yet have a holographic working model for cosmology, but we have the gravitational path integral from which we can try to infer some of the properties of the fundamental model. And the most naive application of this gravitational path integral leads us to consider the Hartle-Hawking no boundary state that, however, has problems. In 4 dimensions, it has sort of experimental problems. In 2 dimensions, in our 2-dimensional model, it has just a theoretical problem. Okay, that's the status. Now I'm moving to this. So that was. I'm moving to the main topic of my talk. This is the Bra-ket wormholes. Okay, and let's be in the 2-dimensional JT gravity here. So as I mentioned above, in cosmology, actually it's more natural not just to think about a state, compute a state, but we want to compute some in observables. So for example, some correlation functions, expectation values of some operators. And for this, we always need kind of Bra-ket of our wave function. Like any observable in quantum mechanics, something sandwiched between Bra-ket. So if we now follow our no boundary proposal, we actually have 2 boundaries. Okay, one for Bra and one for ket, and there are 2 spacetimes to fill in. Okay, and the question is, should we consider connected spacetimes where somehow Bra is through geometry connected to a ket? And that is the thing that's called Bra-ket wormhole. Okay, I think that's quite self-explanatory, the term. And in particular, okay, it is natural, I think, in this gravitational setup to study the following observable. That's called Wigner distribution. The Wigner distribution is a certain Fourier transform of a density matrix that produces a variable, produces a function that's defined on a classical phase space of the system. So why is it good? Because in cosmology, you see, I want to produce from this quantum gravity state some initial condition for then classical Einstein equations. So to specify initial conditions, I need some variables and they conjugate moment. Of course, in quantum mechanics, like if I compute wave function, I can be in position space, in position representation, moment representation. I cannot specify simultaneously position momentum. But for semi-classical states, I mean, I can get close to it. So Wigner came up with this Fourier transform of a density matrix because it's an object defined in a classical phase space that for semi-classical states gives you a probability distribution for your classical variables. From that you can evolve with classical equation of motion. Okay? So here I'm in the immediate space approximation, which is exact for this 2D gravity model. So I just have a size of the universe and P, which is basically like a rate at which it's expanding. You can think of it this way. Good, and now you see, you may say you may not have encountered this object in a context of cosmology, but if you follow these recent developments in ADS CFT, you might have encountered an object called spectrum form factor. And actually, the spectral form factor was considered in the paper by Saad, Stanford, and Schenker. In microcanonical ensemble, okay? So spectral form factor is some object that depends on the two CFT partition functions, okay? So it also object has two boundaries, is Z, there's two CFT partition functions taken at some mixture of real and imaginary times, and then it was Fourier transformed in a way very similar to what happens here. And then with these boundary conditions, there is actually, like kind of answering the question I put 2 slides ago, should we consider those solutions? At least with this boundary condition, we actually do find a semi-classical solution, okay? And this solution is very similar to this solution that produced a ramp in this spectral form factor. I apologize for those who are not familiar with this paper, because then this analogy is not helpful, but for those who are familiar with this paper, analogy could be useful, because metric and dilaton behavior is very similar. So the idea is that we have, instead of cosh as we had here for the scale factor, we have a sinh, and so we have a singularity in the past, but the singularity is avoided by going in the complex plane. And Bra, so this is the contour in the T plane, and this is just this red thing is this time contour, right? And you see, so then we have here again some evolution, and then the Euclidean kind of complex part of the geometry connects Bra-ket. Okay? Very good. So until now we, I think I didn't mention it explicitly because it's common in this JT gravity that you put a boundary at some constant large value of the dilaton. Okay? That's what I was implicitly doing until now. That was not very important. I want just to, I can just say that we can also do something different. We can put this some inflaton field, as we had in 4-dimensionalization model, to kind of get a bit closer to realistic models, and then use it as time variable. Then we have a 4-dimensional phase space. Okay, we have our size of the universe and value of the dilaton, and their corresponding conjugate momenta that I call here L, phi, p, and q. And note that for any of these variables, they define as like an average between Bra and ket, because for quantum mechanical state, you don't have to have the same value of some variable in the Bra and ket geometries could be different. Okay, but for semi-classical, of course, they will be very close to each other, and the way we define both position momenta as an average between the two. So classical equation of motion, they produce this, and then as you see, where b and phi r are some parameters of classical solution, but the idea that L times p is always equal to phi times q. And then our distribution, and okay, it's the details of the calculation in the paper, I'm just giving you the answer. Our distribution at leading order produces exactly this delta function of a classical solution, which is a good sign. It says that the calculation makes sense, and we're actually consistent with having a semi-classical state. We also computed the one-loop determinant from the Schwarzenberg mode, and then in this representation, actually in leading approximation, is some boring constant, but it has an important effect. Okay, so where are we standing now? So we found a solution, right? But there is also a Hartle-Hawking solution, which is a disconnected one. So which one dominates? Okay, so Hartle-Hawking one, Hartle-Hawking one. Is enhanced by the horizon area term. You remember the phi naught, the horizon area term. Our thing is higher genus. It's like a torus diagram in string theory. It's not enhanced by It's suppressed, if you want to, by the in the genus expansion. But our solution is instead from this prefactor is enhanced in particular by a power of L. L is the size of the universe. Phi is the value of the dilaton. Both are large, but here you see L comes to the higher power. So even if L over phi is something fixed, at late times L is enhanced. So for large enough universes, the Bra-ket solution dominates. And in particular, it starts to dominate always before we have a universe large enough so that we can create the strong subjectivity paradox. So the strong subjectivity paradox gets resolved by the Bra-ket wormhole solution kicking in, and then you can actually do this island entropy calculation on the Bra-ket wormhole, and you find that the strong subjectivity is satisfied. Okay, so everything is nice. We have a consistency check, and we found this new solution. So let me summarize. Okay, so we constructed this Bra-ket wormhole solution that dominates over the Hartle-Hawking geometry and gives sort of a meaningful probability measure on the classical phase space. That is, it says that we should get a universe that's close to classical solutions. Okay, that's kind of nice. But it's not. We cannot claim the victory because globally on the classical phase space, our measure is not really normalizable. Okay. There are two types of divergences. One is divergence at large volumes, okay, and another is divergence when the universe is very young. So this divergence, I believe that it is not universal, it's kind of model dependent, and maybe by considering more interesting models we can somehow cure it, okay? While this divergence of large volumes, if we jump to our analogy with the spectral form factor, could be cured or modified by considering even higher topologies that can be enhanced by even higher powers of this universe size. Okay, and then what are the future directions? Is that okay? We believe that our solution can be lifted to 4 dimensions. Definitely with S1 times S2 topology, because basically that's where we can reduce from, and that gives us, I think, lots of interesting opportunities to also, what happens with other topologies. When do we have this ramp-like and factors that are enhancing our contributions for large volumes, and what does it correspond to? Where I take here CFT. I mean, by CFT, it's in parentheses. It's the some would be boundary or holographic more microscopic theory. Okay, so it's not so clear yet what this ramp-like behavior means there. Basically to summarize is that I think that the gravitational path integral allows us to calculate many interesting observables in gravity just using semi-classical gravity, if we're creative enough with using creative and careful enough with using topologies, and hopefully that will give us enough data to start maybe guessing, what the microscopic theory should be. Okay, I'll end here. I'll take some questions if you have any, and then we'll continue.
Questions? Just wait once.
So, how are the Bra-ket wormholes related to matrix models in both the de Sitter and the de Sitter case?
Well, I think it's understood to some extent, at least, how this ramp is related, appears in matrix models in under de Sitter case, right? Yeah. So now, in the de Sitter case, I do not have any matrix model that I would, bet that should describe the de Sitter space. There are some proposals, we can discuss them, but what I'm saying here is that if in the bulk we have this feature that looks like a ramp, then it better mean something in the matrix model. Now, it's not obvious because naively this, my circle, L is the size of a spatial direction, right? So I do not know if we should still, in the matrix model, think of it as more like a, time direction. That is plausible, but that gives us this a little bit strange feature, right? That what is the time direction in the fundamental theory it becomes like a spatial direction in the bulk, right? I mean, that's not something we used to, but it opens So far it poses a bit more questions than answers. I don't have an answer to a question. My point is that if we investigate this further, maybe we'll figure it out, right? But I don't have an answer.
Thank you.
So it's notoriously tricky to cut open gravitational path integrals because of large diffeomorphisms. So for your Wigner distribution, is there some honest Euclidean calculation that can be translated to this, or are you just using this analogy of this looking like a bra and a cat and the wormhole gluing them together?
Yeah, so what I'm doing here, I mean, I didn't describe it in details, but right, what I have in mind is that I have this period of evolution, expansion when gravity is dynamical, and then I sort of glue it like in this near ADS solution to say, you know, maybe if we go here to our real world in my representation, somewhere here, I glue it to just a classical universe where moreover I say gravity is basically not dynamical, okay? I mean, if gravity is classical, it's like more of the same as saying not dynamical, and doesn't lead to topology changing effects. Now, of course, I mean, I cannot, the question, am I justified to do it or not? Okay, and I mean, short answer is I do not know. I assume, I mean, to technically do the calculation, that's basically what I did. I just at some point, I said universe now is very big, so I forget about quantum gravitational effect. Okay, that's what now. You may say that misses some important, I think for some range of L's, that should be good approximation, I think. Now, when L is the size of the universe, when it becomes very, very large, maybe it's again a better approximation because of some new effect, because maybe I can have some baby universe, you know, and like 2 universes instead of 1 universe, and like how do I take it into account? And I do not know yet how to treat this effect. Maybe what we need to do then is to say that we have some, you know, observable part of the universe somewhere here, where we kind of say, okay, we just see there that we project on a thing that the space-time is simple there. But then once we go kind of outside in the spatial direction, we should allow whatever, right? So that should change boundary conditions for my wormhole that I should fix. Let's say here, I should not insist on fixing, you know, the entire length, but I kind of fix some region here, and I fix my semi-classical variables here, and I allow for everything to happen outside of that region. But yeah, it's true. We don't have boundary, right? Space-like boundary ideas. We have to live with it. We need to at some point decide. But the feeling is that for large enough parts of the universe, but not too large, it should be a good approximation to freeze the metric there. But it's true. I don't think anyone has like a much better answer for this. I mean, I don't have a better answer.
Okay, so maybe let's thank Viktor again and proceed to